So I'd like to introduce Steve. And can you hear us, Steve?
Can hear you fine. Good morning, everyone. Can you hear me, Maggot?
I can, yeah. So, okay. Yes, you can go ahead.
Yeah, you're seeing my screen then?
We can see your screen, yes. If the sound is a bit low. If you,
Is that better? That's about it.
there is some echo.
Hey, hold on one second. Let me see if I can fix that. Second, if I can. Settings.
I think we can hear you good now.
Okay. I'm sorry about that. Let me share again. Okay. Can you hear me better now? Is that better?
Yes.
Okay. So good morning, and I agree. This is it was a great segue into my presentation. I am a member of the System Engineering Organization. I am one of the founders of our JPL Digital Engineering Center. Happens to be very synergistic with a couple of the roles I have, which is the Engineering Development Office, which is our strategic advancement initiative. And then I also manage the Autonomous Center, our Center for Autonomous Robotic Systems, which turns out to be a key forcing function in the need for us to improve our capabilities in digital engineering. So why we established JDEC? There's several reasons. One is we need to improve the effectiveness, efficiency, and speed of developing new technologies and formulating advanced systems. Digital engineering particularly enables early and perceptive rapid prototyping of system-level solutions that allow us to do comprehensive trade space development and quantitative comparisons and retire risk early. So it facilitates the timeline in a first-order way. We want to consolidate the digital engineering disciplines across the organization. We have multiple instances of digital engineering practice across JPL, but we aren't leveraging the integration of those silos into a more cohesive development framework and community that can do much more effective system engineering when combined. So we're looking to create more collaborative platforms and engagement across the lab. We want to create a digital engineering infrastructure or a digital engineering platform, so to speak, that allows us to create connectivity and integration of various domain models into a system-level predictive environment and progress that across the lifecycle. A particular focus of today's presentation will be on early architectural modeling. This is an area that I think is one of the more key drivers of JPL, which is especially as we navigate away from legacy technologies and have to accommodate more complex, more diverse, more new types of missions. We want to be able to create and explore a trade space comprehensively, do quantitative analysis early, and arrive at an optimum solution and validate the architecture before we commit to the investment. And I'll get into more of that later. And so we all recognize the space sector is in a state of change. We need to adapt our system engineering practices, which are even our tried and true methods are becoming somewhat obsolete in the context of increasing complexity, scope, and diversity, and not scaling well to the new challenges. And that's a lot of the motivation for establishing JDEC. I'll start with our strategic vision. We've spent a lot of time trying to figure out how we will implement change at the lab. And we determined that there are three major categories or activities that we are engaging in to infuse better digital engineering practices at JPL. One of them is community alignment. We recognize one of the bigger challenges of our endeavor is getting advocacy and understanding and acceptance or embracing digital engineering across the lab. So creating that North Star, getting everyone on board that we have to move in this direction is a big part of our motivation. The second is resource development. We have, again, siloed and ad hoc tool development and methodologies that support digital engineering across the lab. We need to close gaps where we don't have capabilities. We need to combine resources when we do. And so developing that portfolio, that library of component capabilities that we can integrate into a more cohesive platform is the second leg of our our journey. And then the third is that we spend a lot of time monitoring projects across the lab to try to find opportunities where we can leverage our current capabilities and potentially even grow with the project to advance our capabilities. This does a bunch of things. It establishes credibility, it establishes awareness, it allows us to refine our methods and creates a better environment for us to communicate the needs, the capabilities, and gain confidence in our effort. The foundational goals of our center are four primary. One is provide a well-formulated digital models for every step of the project development cycle. So we all recognize that as the development life cycle phase progresses, different questions are being asked and different levels of abstraction are needed. And we want to build tools and methodologies that adapt the level of abstraction to the maturity of the design, but yet build on each other. So we want the connectivity, the traceability, and the evolution of our models to span the life cycle and be agile and low fidelity when they need to be, detailed and high fidelity when they need to be, but be building on each other and creating that cohesive development environment that we all strive for. The second, obviously, is to create that collaborative environment creates a lot of coordination and communication across the domains and disciplines within that domain, having the ability to bring different domains early into the development life cycle, they contribute to the overall solution, including operations and reliability and fault protection and things that typically don't pick up till later. The development life cycle, having the collaborative platform where you can bring component models together earlier into a co-simulation environment allows us to really understand interfaces and trade solutions over a much broader spectrum of technology and create more robust solutions. Early prototyping, as I mentioned, is kind of one of the key themes of this presentation. The ability to create agile but perceptive prototypes early in the development cycle allows us to what we call fail fast, learn early. So we can do multiple instantiations of the potential approaches to understand their strengths and weaknesses and continue to evolve to better solutions. It allows us to create deeper penetration earlier and much more efficient development because we can more or less validate the approach before we commit to any level of investment where things get much more expensive to change, where things get more expensive to change. It also allows us to much better specification of components of our system. This is an area we've been spending a lot of time on, creating a framework for developing executable specifications, much more complete and richer descriptions of requirements on software and hardware that eliminate a lot of the ambiguity that our developers have in using narrative documents and shell statements. Creating executable specifications is a core tenet. And combined, that allows us to identify and retire risk earlier and eliminate unknowns, which facilitates the development lifecycle timeframe. And we, as I mentioned, we all recognize that culture is as important as the technology. We're looking to modernize our approach and establish a digital engineering infrastructure, but we're also looking to train our workforce to be much more digitally fluent and understanding the capabilities that this new paradigm offers, and provide a platform that's intuitive, easy to access, and accommodates, I would say, legacy technologies, but in a new, more connected environment. And a lot of intricacies and nuances there that we'll get into in a minute. Stop me if you have any questions.
Could you go into presentation mode, please?
Oh, sure, of course. So one of the foundational elements of our Digital Engineering Center is the concept of a digital twin. I'm sure most of the audience knows that I'll express the components in the context or vernacular that we use. On the top right, go ahead. Question? On the top right, we have what we call the physical twin or the physical asset. This could be anything from a unit test bed to a system test bed to the INT floor to the flight article. The physical twins are connected to a digital environment through what we call a digital thread. This provides the pipeline that allows telemetry data to be fed into our digital environment, allows the physical twin to report its performance, its health, its maintenance needs, allows us to look at performance of the physical asset over various scenarios and environments. In turn, the digital twin on the top left has capabilities and infrastructure and software layers that allow us to assimilate the incoming telemetry data, to analyze it, to use it to continuously synchronize and calibrate the digital models with the status of the physical twin. And this allows us to do a lot of powerful things. It allows us to tune the onboard system or the flight system, hardware system, real time, allows to adjust control parameters, fault thresholds, et cetera. And maybe even more importantly, it allows us to do preventative actions. By using the continuously calibrated models, we were able to have a much better estimate of the state of the system and to forecast it. By combining observational data with simulation outputs and using mathematical formulations like Bayesian inference and particle filters, we can create very reliable forecasts of the system state. We can project or diagnose potential anomaly situations. We can change our preventative maintenance cycles to extend life, which is becoming very germane in the Mars sample return world. A lot of powerful things we can do with a well-calibrated digital model. Question? Sorry, I keep hearing a little bit of noise feedback. One thing that's not talked about a lot in the digital twin environment is it involves a lot of careful thought about how we instrument the physical twin. So the sensor networks, the topology of the sensors, where they're placed and so forth, creates a very key aspect of the digital twin infrastructure, which is observability and the data acquisition of that telemetry. High bandwidth, highly diverse data is coming across, has to be decommutated and transferred to the system development platform, which hosts the digital twin. And then importantly, this concept isn't just about when we have physical assets, it's meant to encompass the entire life cycle, which I'll describe in the next chart, which is at JPL and within our digital engineering center, we've evolved a digital infrastructure or digital twin infrastructure that's predicated on the idea of evolutionary digital twins. And what that means is that the digital twin doesn't appear when you're in system test or in flight. It's built up carefully from all the digital models that you use during the entire development cycle, including a level we call pre-digital twin, which is really the integrated modeling and architectural trade studies that establish the system solution. And then those models are evolved into different stages of maturity. The developmental digital twin we call is when physical assets first become available, like I can synchronize and calibrate individual components of my digital twin. If you're doing a unit test, for example, I don't need all the physical twins there concurrently. I can slowly build up the fidelity of each component model and then infer from those detailed components more information about the interfaces that my remaining digital representations contribute to the system. When we're in level 3, this is when the first system hardware platforms are available to us, like the system testbed or the integration and test platform. And now we are operating more flight-like with flight-like components across the system. And this allows us to start interacting in a more V&V context. We can use the digital thread to detect trending data. We can automate commands in a command loop. We can project problems. We can automate test shifts. There's a lot of things we can do in the validation world, but most importantly, by the time we're at level 3, we should have a well-calibrated digital representation of the entire system, which allows us to do extended testing. This is a critical component of digital twin infrastructure that allows us to do concurrent extended V&V, which means you're working in a system test environment that is very constrained by the fact that you're using hardware. You've got limitations in shift, you've got limitations in resources. So the digital twin can be used to run extended cases. We can run stressing cases, robustness cases. We can extend to the edge. We can do them fast and rapid. So concurrently with the physical testing platforms, we can do much extended V&V and explore a lot more richness and detail in the system, including probabilistic modeling for autonomous systems, for which this is a key component of. And then finally, the flight digital twin is when we're actually into the mission and we're monitoring the telemetry stream, but assimilating data through what I call a digital dashboard, where we infuse intelligent methods, AI, ML techniques to assimilate the data, to partition it, to learn from it, to increase our ability to understand what's happening in our flight system, especially if there's a high degree of uncertainty, project states, I mentioned, forecast problems, early anomaly detection. A lot of very powerful things happen when you have a accurate and calibrated digital representation of your flight system. The reason yeah, sure, go ahead.
Hey, this is Marcus. How's it going?
Hi, Marcus, how are you?
I'm all right. I have some questions about this concept, and one of the things, I'll try and be brief, although I'm not known for being brief. The JDEC stuff, what can you comment on? Because traditional systems engineering work is messy. And one of the things, and coming from the prior presentation, that can you comment, and you don't have to go into too much detail about taking this methodology and morphing it and making it fit into the messy day-to-day operations, and then maybe convincing the messy day-to-day operations and the people doing the work that this benefits them, so that there is kind of a dance over time that we will converge to, you know, the way this is described right here. I'm just curious on how the status quo, and then maybe how you see this going forward and integrating with that messy ecosystem. You're muted, by the way, Steve.
Oh, can you hear me now? I'm sorry, sometimes.
Yes, you're good. Go ahead.
Yeah, a great question, Marcus. I think I don't have a really polished answer. I think it's going to take a lot of time. Our strategy is predicated on looking for projects to infuse the capability incrementally so that projects start to understand what they can streamline. I would offer that I would rather think about it not as integrating with a messy approach, but reducing that messiness, if you will, by over time understanding how you can create a more incremental evolutionary platform that allows you to create the connectivity and the incremental maturity of the design through connected models. So one of the things we're doing, like on a new project called Endurance, where we are starting with a integrated modeling and simulation platform that allows us to model the entire concept of operations across the entire mission development. Those models don't have high fidelity. They will use kinematics instead of dynamics. They use lower fidelity approaches, but allows us to visualize the entire mission and introduce parametrically things that may influence that mission to a first order. And this is way, in my idea, you can reduce the messiness because it identifies the key trades and the key aspects of your mission development early enough that you can start to inform key requirements and develop synergies with those domain areas that are going to help you solve the bigger challenges, a prioritized list of challenges, which may include system robustness, onboard fall protection, or autonomous systems, or better communication windows and geometry, things that will kind of affect in a first order way how your mission proceeds. And then our goal is to, once you establish that early modeling framework, that you can then connect it and evolve it into the later stages, which keeps a lot of the messiness in my mind, Marcus, has to do with disconnected modeling, where people are off in their own silos doing their work and not integrating with the entire system and the various domains that influence their work. And when it comes together later into the project, that creates that messiness we've been seeing. And we're trying to clean that up by bringing it up much earlier and in a much more collaborative environment. I hope, does that get at your question?
Yeah. I mean, my running trend throughout this whole, so far that I've seen, and then it's going to be a continuous trend, is the people. And you actually had a quote on one of your last slides from BUCHER.
Yeah.
The implication there is just like, it's the people, the views and viewpoints in reducing the messiness is enticing those people that this is a better way of doing things.
Yes.
So that was, I didn't communicate that, but the thought is, it's messy because there's no alternative to getting the work done now. So if you present to the user that this is a better approach, that it makes their lives easier, it will, I won't want to say sold, but anyway, yeah. So you're getting at the essence of what I was saying. Thank you.
Thanks, Marcus. Good talking to you. Good to hear you. Okay. Time check. I know I'm running kind of late. So I'm going to go a little fast here. Stop me. Kind of talked to most of this, but we really see huge leverage and utility in creating this architectural modeling culture, if you will, where we have early in the development's life cycle, we have computational efficiency, where we're looking at macro trends, ability to penetrate early into the system, having a code base that's easy to use and doesn't require high fidelity specialized software prior to need, if you will. Maggie talked about agility. This allows us to adapt quickly to the various integrations and to do probabilistic modeling, as I mentioned, like maybe introducing parametrically like fault rates and fault recovery times from legacy missions to look at explicitly how that affects at a macro level a system solution. So this concept of low fidelity, where you adapt the maturity of your models to the maturity of the design, is a very powerful concept, and we've been using it very effectively at JPL, and is one of the key tenets that allow us to start to infuse acceptance of digital engineering across the lab and address the questions that Mark just brought up. You guys have seen this rubric. We know there's huge advantages to discovering problems with your system early. The cost to change design just grows in orders of magnitude as you progress in the life cycle. And one of our mantras is to try to create the ability to create and validate your architecture and perceive those problems much earlier before you commit to a lot of investment. A quick note on our, we spent a lot of time and money in our initiative organizations to create a simulation architecture carefully formulated based on object-oriented design principles, where each component module of our simulation encapsulates both data and attributes, and we focus on the interaction between those objects in our simulation architecture so that we can easily mix and match and adapt to different configurations within different object classes. It's architected. On the left, you see kind of the system under development, if you will, and the environment it operates in. On the right, you see the control elements in a three-tiered system. We've got the system-level onboard autonomy, which is the deliberative aspect. This is really typically the planning and scheduling and execution aspects that Nick Roquette, who's in the audience, is doing a lot of tremendous work on for Endurance. Our functional level autonomy is more at the subsystem level and encompasses more conventional closed-loop methodologies that apply to mobility functions and perception functions, but the system and functional level autonomy interact carefully to create the overall mission approach. And then we have in the third box the onboard models, the reduced order models of the systems we're reasoning about to help the deliberative engines understand what's being reported from the system and how to adapt its behaviors and commands to what's being reported through the interaction with the system under control. Very powerful. We've applied it to a couple of scenarios. I wanted to show you early on when we were building this concept of this architecture, we wanted to shadow of a couple of missions as a proof of concept. One of the ones we chose was the asteroid redirect mission, the DARTS mission, the double asteroid redirect test, which targeted a binary asteroid system where Dimorphos is the bigger asteroid and Didymos is orbiting around Dimorphos. And we took that system and decomposed it. In the top, you see a very detailed perception and navigation pipeline that was used for that mission. And below it, you see a reduced order representation, which is exactly what Muscat excels at, be able to kind of create enough fidelity for us to understand the basic aspects of the system and do architectural level investigations, and doesn't require all the finite detail. What you're seeing on the right is a photorealistic image of our approach to Didymos, and is representing the lower left, how the modeling of darts was replicated in our system and showed that how we can model the key tenets of the mission in a very agile, low fidelity way. And what it enables is this chart is an example of when I talk about architectural modeling, this is what really is the deliverable and behind our motivation. It's an interesting thought here, or a lot of thoughts here, but it's kind of meant to kind of show you what we mean by the ability to do early trade studies in a perceptive environment. When you look at an asteroid redirect mission, its ability to identify, navigate to, and interact with a very small body in a uncorrelated space with hazards and so forth, there's a lot going on here. And you can see a couple of parameters I chose. The ability of us to do that is heavily dependent on the onboard system ability to predict position and velocity errors, basically. And we looked at a trade, can we use ground in the loop trajectory corrections, or do we need onboard autonomy to do that in order to adjust our trajectory to capture this small body? If you look on the left, we parameterize the assumptions of onboard performance by looking at either very accurate or very coarse, and in between on-board estimation errors and how it affects the architecture of the mission performance. The data cutoff time is the time between the last onboard measurement and the updated commands, which is 8 hours in our model, and the onboard system with an autonomous component for navigation, the time plane is 1 hour. And you can see that when the position and velocity errors are very precise, both methods are appropriate. Both onboard and ground the loop can work to navigate to the asteroid. If you're moderate performance, it would indicate that you really do need an onboard system because the data cutoff method is too coarse and you'll fly right past the body. If you have very weak assumptions, neither approach is utilized or effective. And what this does is allows us to trade onboard complexity and sophistication in the perception system and the navigation system with the commensurate factors that represent onboard autonomy versus ground the loop, and looking at all the various combinations of those technologies to come up with an optimum solution. So the ability to mix and match and look at various approaches to this problem with an architectural modeling framework allows you to do something perceptive and quantitative early in the cycle and optimize your system. We did a similar thing for endurance, where we modeled the entire mission from our ingress point all the way across the South Pole Aitken Basin, about a 2,000-kilometer traverse over 4 years with margin. And what we wanted to do early is look at what are the macroscopic trends that this concept of operations introduces. How sensitive is the traverse rate to fault rates? How sensitive it is to communication windows? How is our power utilization affecting our traverse, and so forth? And a similar thing where we created a object-oriented approach to the mission. The components are very different. The architecture is similar. It kind of was a proof of concept of how quickly we can adapt our simulation framework to a completely different mission, a surface-based mission with high levels of autonomy. And with this simulation infrastructure, we created this, which is at the top left, a little red dot represents the trajectory of the Endurance rover following the flight path that was designed. In the graphs that are shown, we're variously tracking the geometry of the sun and the comm windows relative to our rover position. We're showing distance traveled with time. We're showing our data volume handling capabilities, meaning the rate of accumulation of onboard data and our ability to downlink it without losing data. And then finally, on the bottom right, we're looking at how our RTG-based energy generation system compares to our power demands over the duration. So again, a low fidelity kinematic-based simulation, but gives very interesting and important insights into the various parameters that affect the mission design and can go into trade space evolution. So this is what I mean when I talk about architectural modeling and how an integrated modeling and simulation framework enables that early system engineering, allows us to converge on major objectives, allows various domains to interact early and create that interaction and communication among people that Marcus was talking about, and kind of clean up that messiness in the overall life cycle. We do recognize that we have to continually evolve our simulation capabilities. I mentioned, as the maturity of the design progresses, the questions become harder, they become different, and they demand different levels of modeling fidelity. In the table, I'm just kind of showing the correlation between the various applications and the modeling requirements, where now we need to address much more nuanced, much more complex physical phenomenon like terra mechanics and jitter and very, very complex phenomenon that have to be modeled in much higher fidelity simulations. And we are building our simulation architecture to evolve into that high fidelity domain and to interact with prototype flight software, which is a different capability than what I've showed, where now you're embedding software developed by the software development community with these high fidelity models to get a much deeper, more accurate look at these phenomenon when they become part of when they become relevant in the maturity of the design and when they're needed. And then I finally going to wrap up with a kind of a simulation of what a high fidelity simulation looks like in my vernacular, where you combine we have a Darts D-shell framework. We call it a high fidelity dynamic simulator combined with prototype software to do a very complicated lunar rover simulation, which is combining lighting, perception, hazard avoidance, etc., using an artificial environment where you can introduce hazards and look at how the entire system performs in a very complex and high fidelity domain. But this is an evolution of those early studies, which creates the connectedness and the mission ConOps that assures that the right contextual information is being used as we evolve to this high fidelity representation. And anyway, that's my last chart. I hope it gave it kind of an overview of what JADEC is trying to accomplish and some of the examples of the success we've had. There are several people in the room that have had major contributors to this this initiative, and we have some exciting challenges ahead. But that's the summary of our Digital Engineering Center. And if you let me know if you have any questions. If later again.
Thank you, Steve.
Yeah.
There is a question in the chat.
Okay. Great question. Yeah, I think as I mentioned in the digital twin chart, the major difference in the digital twin infrastructure is the digital thread. The vernacular is still evolving in the industry, but from my perspective, what's unique about a digital twin relative to an integrated modeling simulation framework is that you're actually calibrating the data with physical data, or in this case, I call the physical twin the source of truth. And what digital threads do is allows you to combine observational data or telemetry from the source of truth in the physical twin with simulation outputs and bring those together, reconcile them through continuous calibration and synchronization. So you have a state estimation in your digital twin that is both synchronized in time, meaning it represents the active state of the physical twin, and it's accurate, it's equivalent. And so in the integrated modeling simulation framework, you don't have any real-time source of truth. It's all static in the sense that these are the components we have, and this is what we're doing at the time. And we run it kind of asynchronously. When we're using digital twins, we endeavor to run them synchronously as much as possible as the availability and the connections to the physical twins becomes available. We can use that physical twin to create improved state estimation and, again, early anomaly detection, interactions with maintenance cycles, test generation, understanding where things are most leveraged when you want to do testing. It can automate test shifts and reduce the overhead of expensive INT. There's all kinds of use cases that the digital thread between the physical and digital twins enables that's very different and very separate in my mind from the integrated modeling simulation framework. They're connected in that the integrated modeling simulation frameworks provide the basis for the initial digital twin. And once that is established, then the digital thread is the primary mechanism by we upgrade and improve the fidelity and state estimation embedded in our digital twin. And the other component that I'll quickly mention, I don't have time to get into today, is the intelligent component. The ability to use AI ML techniques to create digital dashboards that can combine heterogeneous sources of information. In addition to the simulation data, we can combine documents, analytics, and other sources of data. And using different techniques, including large language models, we can assimilate that heterogeneous data and output to create a dashboard that allows very rich, very detailed information to the operator and gives them a much better platform to interact with complex mission, either in the test environment or in flight.
Thank you, Steve. Your talk was